Okay, lecture 34 is on dynamics. So last time we talked about statics. That's where the acceleration of the system is 0. This time we're going to consider the opposite, the other situation where the acceleration is not 0. But let's start with the following. Imagine that we're in an elevator, okay, and we're standing on a scale, okay? Now, what are the forces involved here? Let's do a free body diagram, right? And we're going to do it on the person, okay? But I'm going to represent the person with just a block of mass m, okay? Well, there'll be the weight from gravity, which is pulling down, but we'll also have a normal force acting in the opposite direction, and that's the force of the floor, or the scale in this case, pushing up on us, okay?
Okay.
Now, in fact, it will be, as we're about to find out, this is a statics problem because the acceleration is 0, right?
Yeah.
So this is a non-moving elevator, or maybe it's moving at a constant velocity. It doesn't matter. Okay?
Okay.
But the acceleration is 0. So the x direction doesn't matter here. We'll say that the y direction positive is up, which means this weight will be in the negative direction. And so the sum of the forces in the y direction will be equal to n plus w, which will equal 0 because the acceleration is 0. So this means that n is equal to minus w, but w is minus mg, right?
Yeah.
That would be the force of gravity, right? So if we didn't have the scale under our feet and the elevator under that, then we would just be falling, and we know that that would be mg in the negative direction. So this is equal to the negative of a negative is positive, and so that's mg. Okay, so this normal force is the weight that you would read on your scale. Okay,
All right.
so if you were 100 pounds, this is going to be somewhere in the neighborhood of 400 newtons. Now let's consider the case where it's accelerating. So no longer is the acceleration equal to 0. The free body diagram will be the same. We'll have a normal force balancing out with the weight. Okay?
Okay.
But it's not going to balance out because I said it's accelerating. So this time, the sum of the forces, which are the same, right, we'll have n plus w equals m times a. So there's some acceleration. Okay? So in this case, we said that the acceleration is less than 0, so that means that this is in the negative direction, so we'll say minus ma, okay?
Okay.
So you can see, you're going down with some acceleration. So now, what does the scale read? What do you think the scale might read? Is it going to be less or greater than, or the same, as what the scale read when we were sitting still in the elevator? What do you think?
Greater than?
All right, we got two different answers. We got one that says greater than, one that says less than.
I'll go greater than. Yeah, me too.
So you think the scale will read a bit. So if I weighed 100 pounds when the elevator is standing still, or moving with a constant velocity, then you think that if it's accelerating downwards, right? So I'm going down, maybe on the 100th floor, and now I'm going to go down to the ground floor, so the elevator will accelerate downwards, and you think the scale is going to increase the weight that I see on it. Is that right?
No.
No. See, when you start to think about this, then you kind of start to see the answer, right? We need to let our intuition guide us in these kind of things, okay?
Okay.
So what do you think is going to happen to the scale? Imagine that instead of standing on a scale, I was standing on you, right? As the elevator starts to go down, accelerate down, right? I want to move down with a constant velocity. I want to accelerate down, okay?
Yeah.
Do you think that you would feel the weight on your stomach increase or decrease as that accelerator starts to go down?
Increase.
You think both? Okay, so you really don't know, huh? If I'm riding in a car and I hit the accelerator, right? Do I get slammed back into my chair or do I get shoved forward?
You get slammed back into your chair.
Okay, so now the car is the elevator and we're going down. We're accelerating down. So which way am I going to feel pushed? Up towards the top of the elevator or down towards the bottom of the elevator?
Up. For me,
Okay, so if I'm being pushed up some, what happens to the scale?
lighter.
It's going to read a lighter weight, right?
Yeah. Yes.
So our weight, again, is minus mg, so I have that n minus mg equals minus ma, and I can solve for n, because remember this normal force, that's the force of the scale pushing on me. Through Newton's third law, the force that it feels pushing on it will be equal and opposite to this force, right? So n, the normal force, really is what I'm going to read on my scale, okay? So solve for n, right? That will give me that n is equal to m times g minus a. Okay?
Okay.
So the usual acceleration due to gravity, right, it will be less than that. And so the force that I'm pushing with on the scale will be lighter, right? So does this make sense? Before, when we were standing on it, it was mg. Now we're mg minus a, right?
Yes.
So we can see that this one is less than this one, okay?
Okay.
Well, let's consider the other situation. Now we're accelerating upwards. So maybe I'm on the ground floor, and I push the button on the elevator, and I shoot up towards the top. But unlike most elevators, let's assume that this elevator has some constant acceleration that it applies to us as we ride up, okay?
Okay.
So what do you think is going to happen here this time? Is the scale going to read the same, or is it going to be less than like it was when we were accelerating downwards, or is it going to be more because I'm accelerating upwards? Again, think about someone standing on your stomach, right, on an elevator, and then the elevator, like a rocket, shoots up, right? Do you feel more pushing on your stomach as you're accelerating up, or less?
More?
Yeah, more, right? Just like in the car, right? This is the case of the car. So I'm at the bottom of the elevator in my car, and I'm going to drive up the wall, right? But I've got a really good car that can drive up walls, and if I hit the gas, I'm going to feel like I'm pushed back into my seat, right?
Yes.
So that's right. Again, the free body diagram is the same. It's just this time, instead of being equal to 0 or being equal to minus ma, the sum of the forces will be equal to plus ma, because I said that the acceleration is now greater than 0. It's positive. Okay? So what happens this time? Well, we still have n minus mg equals ma. Okay? And I solve for n again, and I get n equals m times g plus a. Okay? Because it's adding to the acceleration due to gravity, right?
Yeah.
We're going to be greater than we were when we were sitting still, right?
Yes.
So we can summarize these results in the normal force when a is less than 0 is less than the normal force when a is equal to 0, which is less than the normal force when a is greater than 0. Okay?
Okay.
Okay, so does everyone understand the elevator examples we've done here?
I think so.
And it's dynamics because the acceleration is no longer 0. So in the statics problems, we always wrote Newton's law and we set it equal to 0, right? Now we have to set it equal to the mass of the system times the acceleration that we experience, okay?
All right.